are estimating this using the short-time Fourier transform, it will be slightly different, because with the short-time Fourier transform, what will happen is that we will take, it's coming from the name actually, it's a short-time Fourier transform. So you, from your EEG signal, that's our EEG, let's not forget that, and we take a short time, so short time Fourier transform. So we take a short time, and for this short window we do our fast Fourier transform. And also it's there is one hint that I didn't mention in the Fourier transform video, which is that you don't want to do the Fourier transformation using a for loop and not even a parallel loop. You just need to use this with the fast Fourier transform because it's much faster and it's really optimized, so it will be quicker. So anyway, we get this window, we apply the fast Fourier transform, so you would have an estimation for each frequency for this particular window. So what this means, if we look at the time frequency plot again, but we are applying the short Fourier transform, we have a window, so we have a center time for this window. So right now we are filling this by putting all the frequencies for a specific time. So we look at the center time, we estimate all the frequencies, so 1 Hertz, 2 Hertz, and so on. So we are estimating all frequencies by the central time point. Okay, and then we proceed to the next window, estimate all frequencies, and we fill that, and we slide this again, and so on until we fill in this for all time points and all frequencies. And the thing is, there is a direct relationship between this and the power spectrum. If you are doing a P-Welch method, if you are taking the average of all of these time points, you will end up with one column representing the average spectrum, and this one column is your spectrum, and it's also according to P-Welch method. Okay, so that's very quickly what is happening with the time frequency plots. With the time frequency analysis, there is also Hilbert transformation that I really like, but perhaps we can make this later, or you can check the code yourself inside this function. And mainly Hilbert transformation and Moulet wavelet and the Fourier transform should give you similar results, but some of them are really handy, like the Hilbert transform are really handy because if you are certain about the band, the frequency band of interest, then estimating the power and phase will be instantaneous with the Hilbert transformation, which means that with the Hilbert transformation you will be able to get a phase and power estimation at every time, which is nice if you are certain about your frequency band. Okay, so anyway, here we are calling this function and we are getting our time frequency plots, and this time frequency is following this order, so that's a dimension order, so it's having channel, frequency, time. So this power spectrum will have channel and then frequency and then time. Okay, so here we are not doing phase consistency, and we're having a baseline period. So here I'm specifying the baseline period. Here I am saying that this is relative change, so here it's applying something like taking the power of the actual EEG minus baseline, and then it divides this by the baseline, and then this will be the relative change. So it's a signal minus baseline divided by baseline. Okay, and here we are doing our baseline correction, and here I'm storing this power spectrum inside of this one. Okay, so right now we have estimated our power for the first condition. We do the exact same thing for the second condition, and we will see how it looks like. Okay, so right now we have this right here, estimating the frequency and time frequency analysis. So let's check the size of this. Okay, so here I'm putting this in a format that that is like condition, and then a channel, and then frequency, and then time. So the reason I'm doing this is that when we are estimating the time frequency analysis, I'm averaging this across trials. So for each condition we will take some trials and we average this across trials. So for every condition we will have a time frequency plot. So that's why we have here two, because we have two conditions. So we have time frequency plot for every condition. Okay, and here we have channel frequency time, because we have a time frequency plot, of course, for every channel as well. Okay, so here I'm just aggregating everything that we get for this particular participant. If you remember, we are looping on participants, so I'm aggregating this for each participant. Okay, so that we can continue with this and see what will happen when we finish looping on all of our participants. Okay, so I'm reaching the end of the for loop here, such that we will look at this, because this should include like the aggregated data from all participants, and each one of them is having two rows, so two conditions in the first dimension. And we can then check the size of that when the code finishes running. So let's check the size of that, and because we are looping on how many participants, we are looping on 5 participants, each one of them contains two conditions, we have 10. So that is correct. We have 10 data in here, and we have so that's 10 conditions, 2 from each participant, and then channel and frequency and time. And then calling our function again, and this time it's similar to what I was doing with the ERP. We can call it twice. We can call it when we estimate the time frequency on the participant level, level 1, and we can call it on the group level when we have the aggregated data from all participants. So we will treat the odd indices as our condition 1, and the even indices as condition 2. Okay, so let's go to this part again and let's continue. And with this one, because we now have a topography, we need to plot this on top of a topography, which is what we will execute here. I am not doing stats, but I'm plotting this. So I can just continue with that. Here I was just tracing some ports, and we can look at our outputs for this. So it will generate many figures, so let's look at each one of them. So this would be our first figure, and this is the figure for the first condition. Okay, so here we have a time frequency plot in this respective location for this channel, and here we have 12 channels, so that's why we are not filling the whole topography, and LV will adapt itself with the number of channels that you have, the actual channels that you have in your data. If you remember, in the ERP analysis, I was doing this with simulated data on 58 channels. Here I'm just using 12 channels, and LV is adapting to this, so it's just showing the 12 channels that we have in our data. And here we can see the time frequency analysis, and this is C5, so that's the time frequency analysis for C5 for condition 1, and this is C1, so that's C1, that's the time frequency analysis for condition 2 and C1. So that's how we read the data. And here we can look at the difference. So that's the difference between condition 1 and condition 2. So that's condition 1 minus condition 2, and we can see the result for the time frequency analysis for every channel. And again, this the good thing about this is that this is interactive, so again we can mark whatever the channels that we want to average together, and we can see that it will produce 3 other figures. One of them is this, and the other one is this, and the third one is this. And I really encourage you to just ignore these labels and go ahead and label your data with whatever you would like to label them. So you can just use this one and just put label and change the label to change this. So it was just coming from my data and what I was doing. So you can just change the label to something else, like time frequency analysis or something. Okay, and you can do the same for all of these labels, so it's easy to change. And that's time on the x-axis, and that's frequency on the y-axis, and that's the color bar is representing power. Of course, power here is relative, it change to baseline. Okay, and we can see that these parts are not estimated, right? And these parts are not estimated because these are coming from the fact that we have specified that we want to use 5 cycles to estimate a frequency. So what will happen if you are trying to estimate 1 Hertz? If you are trying to estimate 1 Hertz and you specified that you need 5 cycles, so you need 5 seconds, but your actual data doesn't have 5 seconds. It has a duration lower than that, then this would be a time point that you cannot estimate, basically. That's why you would see these edges that cannot be estimated, so they have none values. Okay, and here we are looking at the difference. So that's condition 1, that's condition 2, and that's the difference. So that's condition 1 minus condition 2, and we can see this yellow part here. This was not existing here, so it's here it's minus, and here it's positive. So this minus this will give us a negative in this part. So that's nice to look at in our data, and that's perhaps something happening in this frequency. Okay, so we can also still use this without closing anything. We can just look at the grand average and just estimate these figures again. Look at the first and the second one and look at the difference. So that would be the first one, second one, and here the difference. And now it's saying it's the grand average of all channels, and we can see differences here. Okay, so that's how to do a time frequency analysis using lively vectors. I hope it was helpful, and please, if you have any questions, go ahead and comment below or send me an email. And next we will be looking at intertrial phase consistency, and we will go on with our pipeline and analyze this VCI competition data further, and continue with our lively vectors tutorials. Thank you so much for watching this video, and stay tuned for the next one.